Welcome everybody. I'm Amrut. I'm a senior researcher at the Indian Institute for Human Settlements, and this is our eighth. This is our eighth Let's Talk Spatial event. Thanks to ENGEO Analytics and Jyotsna for hosting us here. Before I hand it over to her just to explain about what ENGEO is, just a quick story because a few of us have asked how Let's Talk Spatial started. So basically last year around August or something, Aman and a few others reached out sort of to see if there's an existing spatial event or spatial meetup group in Bangalore. And sometime back there was one. It's called ENGEO Bangalore, headed by Namboothiri, but that slowly sort of lost its steam. And then we thought, okay, there's a lot of industry and academia here in Bangalore for spatial stuff, so we should probably have at least once in a while a meet and greet to see if there's some exchange of ideas and things like that. And then somewhere or the other we just met up at Satyuk, yes. We met up at Satyuk with a huge audience, so like 35 people already on the first day itself. Although a lot of them were Satyuk guys itself, but it was okay, they're all our friends, so it was fine. But yeah, we had it then, and then over the years, over the months, hopefully years, we started going around all other industries. We usually reach out to academia or industry to see if they're interested in sort of hosting a meetup, and we also give a small slot for them to discuss about what they do, is it open source or not, anything, whatever falls under this. And then we reached out to speakers to see if it sort of falls within the theme what we discuss about. And usually the theme is about, if there's something trending happening, or if there is, for example, data science or something really cutting edge happening, we usually have that as a whole theme for the month. Or if there's very standard stuff that is in progress and there's a lot of motion behind it, there's machine learning and stuff and all that. So we use that as one of the themes for the month as well. And then we just reach out to people on LinkedIn, Twitter, see who's interested, and almost everyone is interested. And it's a good sign that at least in Bangalore there's a movement for spatial again, and hopefully we can start reaching out. And yeah, so this is our 8th event after all of that. Hopefully we can keep this continuing. And then, so today's event is all about emerging technology and trends in geospatial domain. And before we start out, I'd like to have Jyotsna just to talk about ENGEO, what's it all about. Yeah.
Hi. So thank you so much, Aman, and Let's Get Spatial.
This is the mic.
Okay. Joining and organizing this event. So my name is Jyotsna. I'm working at ENGEO Analytics. It's a one-week-old startup, so this is very new. So I wanted to have this event basically because I have a consulting background, and I'm interested in starting a startup that has with focus on GIS. So I think the most recent bit of work that I've done that may be interesting to you all is that I helped set up the Singapore government's carbon tax audits. So I have quite a bit of experience in terms of carbon tax audits, sustainability reporting, GRI, TCFD, and I'm looking to build a technical team over here. So I'm hoping that this event is something where I can network with a lot of you and we can work together and collaborate in the future. So ENGEO Analytics will primarily be focused on just GIS-based APIs. So if anyone has any experience in that and you want to work together or collaborate, please do let me know, drop in. Thank you.
Thank you so much.
The robot holding all of this gadgets around.
No, you leave it.
Yeah.
Flying robot.
Cool. So thank you, Jyotsna, for all of that. I think usually our let's say our agenda is that we start out with all the talks, and then towards the end of it, we just keep it open so people are free to talk, exchange ideas, share business cards if that is still a thing. So yeah, that's basically it for how we sort of do all of these things. So our first speaker is going to be Krishna. She's a data science manager at Satshara. I'll just give a small introduction. So after completing a bachelor's in avionics engineering from the Indian Institute of Space Science and Technology, Kothandhapani, Krishna joined Indian Space Research Organization in the capacity of telemetry engineer for the GSLV Mark III launch vehicle project team. After 3 years at ISRO, she went to grad school at the University of Notre Dame, Indiana, and completed Masters in Electrical Engineering with a specialization in applications of system theory. Subsequent to this, Krishna has completed an AI fellowship with Insight Data Science, San Francisco. Since then, she has been working with Stature in the data science team, exploring the numerous applications of geospatial data to derive decision intelligence. So Krishna will be presenting the data science for geospatial data as a talk for today. So Krishna, if you don't know.
Hi, Krishna.
So,
How net? Let's see.
Yeah.
You want to start? You're comfortable with that?
Yeah, this is good.
This also might be required.
No, you can actually wear this. Keep it in your pocket. Keep it closer. Can you test it?
Hi. Is this better?
Yes. Yes.
Hello. Hi. Thank you, Jyotsna, for inviting me. And yeah, so before I get started, I would like to know how many of you are from GIS background and data science background? GIS? You're all GIS people.
Yeah.
I don't know. But how many of you are from data science? How many of you have done data science? Yeah, like a lot of Python coding and stuff.
Yeah.
So maybe this is not exactly relevant for you. My target audience, what I had in mind was people who are from GIS background, but they want to explore data science, but they have a sort of maybe like some starting trouble, or they do not know what the challenges are, how to get started with data science and how to get started with Python. That was primarily my theme. So it's not an emerging trend. It's not exactly with the theme, but it's for this sort of bridging the gap. So what I have tried to do is put together some very basic functions and modules to solve a simple problem in GIS, with a simple and very popular problem, which is the land use classification. How to do that with Python using some basic functionalities. So sounds good?
Yes.
Right. So yeah, let's go over. You all have some Python background.
Just the basics.
Just the basics, right? No, basics is good. I think with the basics we can get started for sure. So yeah, what I'm trying to do is an unsupervised learning approach for land use classification. So very basic definition between supervised learning and unsupervised learning. Supervised learning, you have labels. So if there is a cat and dog classification, basically you name all the cats as cats, all the dogs as dogs, and then when the machine sees a new cat, it knows that it's a cat. But in unsupervised learning, you don't necessarily have the classes defined. The machine is trying to figure out what could be the different classes. So let's get started. So this is my Jupyter notebook, and whenever there is a function, I will switch to my function where the actual calculation is happening. So yeah, first of all we ignore the basic. Let me just verify I have my QGIS open. Right. So I have a bunch of raster images of Aurangabad district saved in my local, and I am viewing that in QGIS. So this is the Aurangabad raster. Now this is a multi-band raster. It has RGB, NIR, SWIR bands. I can just quickly open that up and show you. So it's a multi-band image with RGB, NIR and SWIR band. Yeah, SWIR band I believe, yes. So these are the input files I have saved in my local machine. Now we know what separates a raster from any normal image is the metadata that comes with all the projection, the different bands, what is the data type, what is the extent. So you can easily extract that using the metadata information. And then we proceed to look. So when you open any raster image, it's at the end of the day, it's just an array with numbers, right? So we can always read it into a NumPy array and use any sort of array operations on it. Any matrix operations that is possible for any other functionality, you can easily do it on the raster data. All you have to do is read it into a NumPy array. Now, how do you do that? There are a couple of important libraries that we work with in Python, GDAL and Raster.io. So, if I were to take off all the input files, I take one of the files, and if I have to read it into an array, you will see this is the and this will match. So when I go here, so this is my base raster, which has width and height 13595 and 14272. Now when I am reading into an array, that's exactly what I am getting. I get an array of the same shape, but now it's just, so if I have to quickly display that. So this is the kind of information you will see. I mean, there are numbers inside. What you're seeing is the boundary. So that's why it's just 0. So you can easily read it into an array and do any sort of operations, any matrix operations. I mean, the way you would do in QGIS also, raster bands can be added, subtracted, looking for a specific number, etc. All those operations you can do it in NumPy using an array operator. So that is raster file. Now what I did was, since this Aurangabad district, so this is what I am looking at. It's a large area, and it's, if I had to perform all the operations that I want to on this large area, that would take up all the time. So instead I decided to go for a small shapefile, where I zoom into this much area, just a very small area in the raster, where we can do better analysis. So this shapefile is, so that's the shapefile I'm calling here. And now in QGIS also we have this operation of putting a shapefile on top of a raster and then clipping out the area of interest, right? It's something we routinely do in QGIS. And again, we have a function for that in Python. So what we have done is, what I have done here is, I have taken the shapefile and all the input files and then clipping all the rasters to that shapefile extent. So now what the output would be, so these were my original files. I'll just take out all of them. So this was my original file, 2023-0109 Aurangabad. Now I apply the shapefile on it, which is this much small area, and by using the clipping operation, I get the clipped raster for the same file. That much area. Just a small area, so that it's easier to analyze and run the operations that I want to in the given time. But now let me just, I will circulate these codes. I will circulate the notebook as well, so that you can like just copy paste the contents for if you want to explore further. So this is the good thing is, when you're working on QGIS and you run a clip operation or the zonal stats kind of operations, Usually QGIS also works on GDAL. So you will see which GDAL command is running in the background in QGIS. So you don't even have to search for which command should you be using. So when you look at the clipping operation QGIS, this is exactly the command that is running in the background. And that comes in the log file. I mean, when you run an operation, you get a log file in QGIS generated, right? So you can easily get this command. So you just use this command and you give the original input file, the output file and the shape file, and you're good to go, and you get this clipped raster immediately available. Now, well, I don't have to talk to you GIS people about the indices. So these are some of the indices I have tried to extract from the file, simply because it had NIRR and SWIR bands. I thought I'll look at NDVI, GNDVI, NDWI, etc. So, I mean, we know NDVI is the vegetation. I mean, you are all familiar with NDVI and NDWI, right? So NDVI looks at the vegetation index and NDWI looks at the water index. So now what I decided to do was I calculate these indices from the rasters. Again, this is something we can do in QGIS by doing the addition subtraction operations of bands. It's exactly the same thing that we do in Python as well. We open the raster and we know the blue, green, red NIR SWIR bands are in this order. So you just extract them and then you do NIR minus red by NIR plus red, green minus NIR by green plus NIR, green minus SWIR by green plus SWIR gives you MNDWI. So the very same formula that you see here, I just write it out and then calculate the corresponding indices and write it into respective rasters. So the writing raster part operation is happening here. So you will see I am toggling between GDAL library and raster.io library. So the to show you real quick what is the NDVI, and now all of them. So that operation is happening here. Now let's open the NDVI. So the NDVI of that particular file is now generated. I can zoom in, but then we all know that a higher NDVI value corresponds to the farms, which is visible here as well. It's in grayscale, but I'll show it better here on this side. So that's exactly what I have done. I have calculated all the indices for each and every raster and it is saved in the respective folder. Now the next operation. So if you think about it, we have done multiple operations on rasters. One was just reading it into an array, calculating the indices, clipping to a shapefile, and now let's see how merging the rasters are possible. So which is, so now after calculating GNDVI, MNDWI, NDVI, NDWI, etc., I want to stack them all into a single raster. So the operation yes. So basically I'm reading one of each of these files, one NDVI file, one NDWI file, all from Aurangabad of the same day, and then merging it into a single stack, into a single raster where NDVI will be my 0th band, NDWI is my first band, and so forth. And then I write that all into a single raster. So that particular raster is this generated here. So this is a single raster. Already you can see the features emerging, right? Now that there are, now this is the topmost band. We will look at the individual bands on this side, but you can already see the sort of features that are emerging here. So this is that band. If I go to look at the band, we know that NDVI is a vegetation index, and NDVI would give positive values where there is vegetation and negative values where there is water content. So we have seen here that this is a water. This is a water body here, and there you can see that the NDVI value is negative, and wherever there is higher vegetation, there is a positive value for NDVI. And the same, if I were to look at MNDWI or NDWI, for example, NDWI is the water index, so wherever there is water body, you would expect a positive NDWI value, and wherever there is soil, you would expect a negative NDWI value. So we have done the raster splitting index calculation, and now we have merged it all into a single stack. Now when we do analysis when we do the data analysis, performing a lot of operations becomes easier when it is a 2D array rather than, now we have the multi-band raster in which one band is NDVI, one band is NDWI, and so forth. But the way we do calculations, even if we have to compare one pixel's NDVI value with that pixel's NDWI value, we are a lot more accustomed to doing that on a column basis when we are doing data operations. So if I had one pixel and I see the corresponding NDVI value, corresponding NDWI value in that sort of columnar fashion, in a table fashion, that makes my life a lot easier to perform n number of operations and comparisons. So what I have done is put together a small module to convert the the multi-band raster, into a very clean and neat data frame. So, and that is a very simple function if you look at it. Basically all I have done is I have opened the raster and I have just flattened it out, basically converting a 3D to a 2D. That's just a flattening operation. And since I have given the column names already, NDVI, NDWI are the column names. So for each column, the corresponding band gets added to the column value. So instead of seeing it as an array, now you get it in a columnar fashion. So this is the data frame I have just created. And then if you look at the so these are the different pixels. So and these are the pixel numbers, and for each pixel number, what is the corresponding NDVI versus NDWI. Actually, when we look at this itself, we can get an indication. NDVI value is positive here and NDWI value is negative. So this is probably a vegetation pixel. And here NDVI value is negative but NDWI value is positive. So this is probably a water pixel. If you have to do some simple calculation here, how many pixels are there, what is the value of each, what is the histogram, what is the distribution, you can immediately do it. Even if you had to download this into a CSV and do some Excel operations, that becomes very easy at this point. But like I mentioned, what I'm trying to do is unsupervised learning method for land use classification, and one of the simplest and most direct methods to do that is k-means clustering. Are you familiar with k-means clustering?
Yeah.
So k-means clustering, what happens is if you have NDVI, NDWI, MNDWI, all these values, we would assume that the pixels that belong to a certain category would have similar values for NDVI, NDWI, etc. Right? And that's exactly visible here. Even from here, if you had to do manually a visual inspection of what is happening, and if I had to combine all the positive NDVI values, all the positive NDWI values separately, I think I would be onto something. I would be creating two categories of vegetation versus water. But now I'm talking about just two columns. I think that is still manually doable, even if I had to put all this into an Excel sheet and I create some rules. I put NDVI greater than 0, NDWI less than 0, and if create some if then else condition even in an Excel column, I think I would see the classes emerging. But then now we are only looking at these many indices and these many bands, but imagine there are 10 of them. It's not possible to come up with rules that easily. So there is this data science concept called clustering, in which all the pixels, in this case pixels, but otherwise data points, all the pixels that behave the same way in all the different features are combined together. They form a neat little cluster. So spatially you can imagine, right? If I had, let's think about a space. We have in Bangalore, I want to cluster the households based on the nearest distance to the bank. So basically I have a bank and all the houses that are closest to that bank will be clustered around that bank or near the metro station, something like that. Now how do we manage that? We calculate the distance between that particular metro station or the bank to all the households, and with the household and whichever bank has the nearest distance to a house gets mapped to that. Now imagine that in a data in a high dimensional data space. You have all these NDVI and NDWI values, and all the points that are closest that form a neat little cluster, they are combined together. So clustering again, I mean all this distance calculation, everything that I mentioned, we don't have to do it. Python already has libraries for that. So there are k-means libraries, or there are other clustering approaches as well. There are other classification methods. But then if you can think of the use case, so like, I mean, if you have reached up to this point by using data, by using all this GDAL operations, and you are at a point where this is your use case, and if you just search, Python usually has necessary functions. You don't have to write it from scratch ever. So mostly. So this is a mini batch k-means library in which you just have to input what are the features based on which you want to do this clustering. And here I am picking number of clusters as 4 just because I do not have that many features, so it will be difficult to distinguish. And I'm just running a clustering operation. Now, so this is the clustering function. I run that. Now the output of that is the data frame with the cluster. So let's look at that cluster. I will comment this out. Right. So like I mentioned, I have created 4 clusters. I mean, this is not, this doesn't necessarily have to be 4. It will depend on your use case. So there are 0, 1, 2, 3 classes. And if you look at the class 1, this is the NDVI value, NDWI value, etc. Class 3, if you look at both the class 3s, you can already see that they look similar, right? In terms of the indices, NDWI value is negative, NDVI value is positive. I can run more. Yeah, you will see that all the data pixels belonging to the same class behaves similar. So here cluster 1 has a certain performance, cluster 0 behaves in a similar way. And now that I have done this clustering operation, I am just going to write into an output raster. Now let's look at the output raster. So cluster.tif was created here. Okay. 0 is not a no data. 0 is one of the clusters. Why am I not seeing 0?
Symbology to become plus.
Yeah.
Yeah, you just need to add another 0.
Become the plus button, delete plus. Turn to 0. And the value.
On the left.
Yeah, great. Thanks. So now these are my 4 clusters, 0, 1, 2, 3, and you can clearly see how the clusters are formed. Now if I had, so now I know that I clearly know class 2 is the water body, and if I were to look here, what was cluster 2? So cluster 2 was NDWI value is positive, NDVI value is either like very minimal or tending to negative, GNDVI is clearly negative. So that was the cluster 2 characteristics. And now even if I had to zoom in anywhere, like small water bodies I see here, let's see if we are right.
Scale law, zoom out to satellite. Now the Google satellite is on the top.
I think it's not loading fast enough.
Tiles are
Yeah, tiles are not zooming fast enough. Yeah, but I hope you get the idea. So by doing the band operations and the simple clustering operation, we were able to separate out the vegetation class from the water class, and we can then take that output, and if you have to do some simple land use classification, it's pretty straightforward at this point. So yeah, that's my presentation.
I have
Time for some questions.
So I've also tried this. So there are a few issues. Now when you scale it to like large satellite image, the whole satellite image, I think k-means will fail because
yes, k-means will fail. So for that, which is specifically why I took a small AOI. Now there are different libraries. Facebook has a k-means library called FAISS, FAISS. You can look that up, which performs a much better, more efficient clustering operation. Or you can do it in batches. There are mini batch k-means clustering, not just the simple scikit k-learn k-means. So there are optimized libraries for clustering operations. And also it's not advised usually to do clustering on the basic bands. It's always advised that you create these features when you know. See, GIS is something that you have subject knowledge of. It's not just a random data set. So you know what you're looking for. If it is to separate between vegetation and water, then just pick NDVI, NDWI. Just select the relevant features and then do the operation. So these two
also
things.
you were using mini k batch.
I was using mini batch.
So does that help in?
Yeah, that helps. That helps in better memory utilization. Also, Facebook has a library which creates multiple threads. Like basically you can engage more CPU utilization. So that will also be fine.
Any other questions?
Yes, so I have one question. In these kind of problems, usually when we are trying to cluster, for smaller cluster, when you try to kind of polygonize it and export the GeoJSON, for smaller cluster, the polygonization, there are a lot of problems. Have you ever tried that?
Oh, I see what you're saying.
I mean, it's a cluster and export it as a GeoJSON.
I've not tried that.
Yeah, so I've tried that. So usually I think there's
it becomes a cross.
Yeah.
A lot of issues.
So for some, not for this specific application, for some other application that we have tried at Satcher, for example, farm boundary generation, right? If you are going to look at farm boundary and then if you were to just create polygons around by edge detection or something, then again this problem will happen because we are not getting the right polygons, and that's why you are not getting, the vector file is not proper. That's why you are not able to export at this point.
No, so it was like assumed like this. So if you use a segmentation algorithm to segment the farms, right?
Yeah.
And then you try to export create a boundary out of that segmentation, right? For the smaller farms, it usually creates a lot of problems. So if you know anything.
No, we have tried this with farm boundaries, and the farm boundaries in India is very difficult to work with. So we have also put some thumb rules for it. If we see like 3-4 points, then how to make the connectivity outside the segmentation.
Okay.
Using image processing, that's something we have tried. But at this point, I think you should try GeoSam. So
now it is working very well.
I know. So segment anything model that they have put out, there is a GeoSam specifically for GIS. So we were testing it out at Satcher, and it's crazy how they are.
So does it solve the problem with the smaller farm boundaries?
It's not perfect,
okay.
but I think we can train it also. So, but it's working well as far as
all the research of all other students have gone in vain. In this just one model. All those who were doing research in the field of segmentation, now they don't have to worry about. Their job is taken away by the SAM model.
Homework is done. Any
So-
other questions? So I have a question. So we have used NDVI and another registration, right? So
Yeah.
Is this like why have we used like 2 types of registration?
No specific reason. This is just to show 2-3 features, and I wanted to pick a very minimal. Otherwise, I know I wouldn't be able to run it fully during this time. So that's the only reason. No, nothing.
So I have a question more on Python versus packages like QGIS. So what are the benefits of going? So QGIS is also open. Python libraries are also open, but if anybody is starting off, studying these types of data sets, how do they know where to go first, and when should they graduate to Python? Should they graduate to QGIS? And what should be?
If you have only 5 rasters to work with, still use QGIS. But when you have 550, we don't have an option, right?
Okay.
So, but I think when knowing QGIS helps you understand the data and how to work with the different functionalities, and then Python would just become the tool. So if you know the relevant functions, which like I said, I would circulate this with Aman, and you can keep it. So basically, if you have to just do the reprojection, that's something that we always deal with in GIS, different projections, how to stack, how to clip. If you know some basic functions, then you can always plug and play.
So it's more like the scale problem. That's only the time you need.
That is one, yes, but then in QGIS you still cannot do more, right? You can only do some raster operations, you can't do machine learning.
So I think for that I will also suggest you to explore Google Earth Engine. It's a good intermediate.
No, what I'm asking is again for benefit of everybody, because
Scaling
even
up
we are
and
using
some-
Python. But the key thing is based on the problem or the phase in which you are in a project, choosing the right thing. Many times people may just start off with Python, get stuck. Then coming back to QGIS sometimes is not an option. They've already done too much work there. They come here, setting up the project and stuff like that. They just go fully there and get stuck. So many people have seen they start the project in the wrong path, like I'm fully pro, and then when they come back it's too late, and like especially if you have a thesis submission to do, they're like, okay, scramble, ask everybody in the world who can answer this, go on like a subreddit, go here, go on Stack Exchange, ask questions. So one more question related to this is, so I think there's lots of this Python packages allowing you to control stuff that happens in QGIS. Take the data out, do the processing separately. So how does that feed in? Where does that work, especially like at scale? Is it feasible?
I personally have not done that at scale. I only use QGIS for just visualization or just to get the feel of things, and then go back to Python for the actual coding.
Okay.
So, but yeah, I know what you're saying. It is possible. You can sometimes, when you have a quick fix and all, we still go to QGIS. You have to quickly extract a shapefile. It's easy to create a layer. Then we still go to QGIS.
And something just to add to that, something that we tell our students also is that start off with QGIS, because having a fundamental idea about what GIS remote sensing is, and you visualize it by buttons and tools, help them sort of build that narrative on how do you now do the processing for whatever NDV or anything of that kind. So, and the thing with QGIS is it's very nicely documented. So, if there's something that they can't understand by just looking at the buttons or understanding the concepts of remote sensing, they can always go into the documentation part of it and see step by step what each of these things do. And then once they reach, so the scale problem is very unique because QGIS is limited in terms of scale at the core level itself. And since it's built on Jira, there's a way to sort of integrate Python within QGIS itself, externally as well, and then scale it up based on whatever your hardware is. So we have done that quite a bit. And that works excellently, there is no issues with that. So that's the boundary line that we draw. If you have to create 5 maps with 10 or 20 data sets, QGIS is okay, like 1 day. But when we have to create 365 maps for continental level analysis and stuff, we use the same model, but just put it into Python, run it. So literally that's the only step for at least mid-level and a little bit higher level experienced folks. But with beginners, we always suggest QGIS to start. Python is only when they're like, oh, I want to learn programming, I want to get a job. That sort of motivation when it comes, it's good. They're like, okay, you want to program? Fine, go ahead. Like, no, there's no problem with that. They can do that. So, yeah, so that it depends on, I think, a little bit subjective on how each person is.
And where do you start? I personally, I don't have a GS background. I am from electrical engineering and a data science background. So I learned QGIS after I
think that's also another unique thing. So after that, when you actually see all of the different mechanisms of how a software works, you'll have a different sort of mentality of running programs. Yeah. So your code, writing the way you write code changes, the way you write documentation changes once you start from programming to a software level. So I think both have its own benefits. It's just sort of experimenting and seeing what it is.
I think one more thing to add on top of it, if you actually are creating some sort of a product, right, which is automated, in that case, QGIS is a lot better. They will
I think it works.
Run in the headless mode.
Yeah, nowadays people are actually using it.
That's great.
So it's completely controlled.
So fun story, this was the first model that I was working on to test with SkyServe. When we were collaborating. So land use classification, we were just testing out the capabilities.
But there are still a lot of intermediary bands that you have, like you showed. You actually saved the NDVI bands.
Yeah.
And then again took them, read them again, and then.
It's not needed actually. You can calculate and then directly feed it
But
into
again,
the system also.
There's so much memory in that is you're just storing on RAM.
That's what you can you can choose to delete after each operation. That's good. Or you don't even have to write the NDVI raster. You can save it in the RAM and then directly take it forth.
But now we're trying out with high-res imagery, and then even if you load like a small patch of it, that's not even.
Those are the emerging trends that we have to sort of work on.
Yeah, but this is a good starting point. From here, you have to take to multiprocessing, batch, high-res.
Yeah.
So that.
So, follow-up question if you have time.
Yeah.
So, say for example, I want to build a front-facing with the same thing. I want to showcase it to clients, right? When we have, like, say, filters and stuff like that, you can move across, say, state boundaries and stuff like that. Does QGIS support that kind of functionality? Like where you can post it?
I mean, so there's something called as PyQt, So
Okay.
Qt is a library that is used to build the interface for GIS itself.
Okay.
So yeah, so that's it. So you can use the Qt library itself. You can host it. You can build your own front end for that. So
Qt.
yeah, PyQt is the thing. It's written in Python.
Okay.
So if you are good with that, you can go with
So
that.
that works out as well as your data scientist.
Yeah,
So,
so then yeah, you can use interfaces like that. So the thing you have to remember is if you have to do a lot of GIS processing on that, you rely on some of these packages that may not be available, for example, on the web.
okay.
So you'll have to have it running on a head server like Jyotsna or something that has to be there for like high level processing. So
Okay.
it won't be a, let's say, fully functional web application in that sense. But you'll have to have some trade-offs when you do that.
But are there other options in the market?
I mean, if you
Because we personally use ArcGIS online and it's worked for us fine. It's just that like the idea of sort of like machine learning becomes a little difficult, right? Because the people who do the GIS are different from the people who work on the machine learning side of things. So we have an issue where we can't talk to each other. But is there, say, like a middle ground, so to speak?
There is one I can suggest, so that's called as QGIS online.
QGIS?
So that's very similar to ArcGIS online. So that's a paid version also, and you can get a paid version for 5 GB.
But we can post it and then run it.
Kind of, we can post it. But that's not like fully mature. It is basic.
But if you're looking to build a custom front end, I don't think you should rely on the way QGIS is built. That's
definitely. No, because like from the basic introduction here, it's pretty clear that that won't work out.
Yeah.
But say we want to set it all up and essentially, what I'm trying to ask is there like a Power BI GIS solution? So,
Yeah, I don't think as of now there are any, other than the proprietary SV thing, it's hard to find at least open.
I think there's one which is called as QGIS to 3GIS, something like that.
Yeah, the same again.
Yeah.
Yeah, that thing.
So
So it works,
but it's
it
not
is similar to ArcGIS
ArcGIS
online.
online.
Okay. But can we do the same thing in say ArcGIS? Because we work with the ArcGIS on an API. So
That's
that's
the ArcGIS, I don't know anything about ArcGIS.
okay. No, also we've tried really hard to get rid of ArcGIS. It's super costly. We'll try to.
I think they have some ArcPy or something.
Yeah, probably there.
No, that's what. But what we're using it for is just to like update our backend data sets for like visualization. That's all.
Maybe you should check with Merlin. There's a company which is a third-party company which is doing very labs for you over features.
Oh, okay.
I think we also use R, like R
Shiny.
programming language. So within R itself is something called as the R Shiny package. So we use that to build basically front end, and all of our geospatial data sets either live on GeoServer or on a Postgres database or things like that. And then we just use R as a front end to just build a front end and also the logic within that. And it's very flexible if you have a background in R, because R is one of the strongest programming languages in statistical analysis. And all of this is basically the mother of stats. So
But how has your experience been with R Shiny?
it's not easy. As in, for geospatial it's easy, but R Shiny itself is a learning curve. So I mean, learning the way R works is one thing that you have to know. That if you have an idea in Python, then R is good. But R Shiny is when you need, like, let's say, a full stack dev sort of background. So you need to know how logics on the server work, how front end also basically. But yeah, it's a slight bit of learning curve, but it's worth it. I mean, I've been struggling with it for a while, but it's fun.
I think it's the same with Python and Streamlit.
Yeah, Streamlit, yeah.
So basically, it's not necessarily no code, slow code sort of situation.
I mean, no, I don't think there is any currently no code scripting for all this. Yeah. Cool. Thank you so much, Krishna. Have a round of applause. Before we go ahead for our next talk, we'll also do a small icebreaker session just to introduce ourselves to ourselves. So we can start from the back. Just tell me about yourself. What do you do? Where you're from? Whatever you want to talk about yourself.
Hello, I'm Parimal. I'm working in IIS Bangalore as a content developer. I mostly work with smart city.
Mostly work with
Smart city.
Very good morning all. I'm Raghavendra SP. I'm doing MTech in Geoinformatics at Karnataka State Remote Sensing Application Center. I'm in the final semester.
Hi, my name is Donald. We work for GKVK. It's a government project where the project is called Revolve. It is rejuvenating watersheds for agriculture through innovative development. We use GIS and satellite images to find out the soil nutrients and the soil profile and suggest what is the most suitable crops that can be grown in the rural Bangalore and other districts in Karnataka. So me and my colleague here,
My name is Subramanya. I am from Shivamogga, and we are in the same project. And we use softwares like RGS 10.8 and RGS Pro, Radars Imaging, and QGIS. So what is already said?
Morning, everyone. My name is Simon. So I work for a company called Saskin. I'm looking to the ARM firmware development for ARM-related applications.
So what do you have?
Firmware development for ARM-related, ARM code.
Okay.
ARM code-related applications.
Hello everyone, I'm Mapurva. I recently completed my Masters in Remote Sensing and I'm currently working as GIS intern at Skylar Post.
Hi everyone, I'm Shadana. I'm working at Airbus as a software engineer and I'm here just to explore what geospatial area is.
Hi, I'm Jyotsna. If I met some of you earlier, I work here. But before this, I used to work at Ernst & Young in Singapore, where I was a sustainability consultant, and I have a biochemistry background.
Hi guys, so I'm Gautam. I'm working here as a founder's office in SkyServe, and I take care of business development. Before SkyServe, I had my own startups. So one of them was into drones, called Infinity Drones, and we are also into this aerial mapping using drones and surveillance.
Hi guys, I'm Adithya, one of the founders of SkyServe. I work there as the chief of product. Before that, I worked as a systems engineer on a satellite building project. So most of my background is aerospace, and it's probably 2-3 years before starting this company that's when I got into geospatial data and sort of getting speak more about it.
Hi everyone, I'm Rakshit. I'm an alumni of IT Madras, and currently I'm co-founder and VP product at Galaxy Space, which is a space tech startup building multi-sensor optical satellites.
Yeah, hi everyone, this is Mohammed Faizan. I am working as Geospatial engineer at NTA Mindtree. I am mostly working on R&D and agriculture.
Hi, my name is Deva. I work as a senior GIS engineer at a location intelligence-based company called LifeSite.
Hi guys, I'm Revan. I work as a data analyst in a company called Catalyst Management.
I am Rahul. I also work as a data scientist at Catalyst Management Services. We generally work across the impact space, where most of our efforts right now are in tech and livelihoods. So our tech stack is Python, ArcGIS, and R. And currently, we're actually, the reason why we're here is also we're actually looking to partner with people and to hire, so to speak, because we have a few projects in the pipeline. If you guys are, any of you are interested, please. Thank you.
Hi, I'm Santosh. I'm working as a data scientist in Geospatial Analytics. Me and my colleagues. And like Geospatial Analytics, we build like different products related to climate and atmosphere. So apart from it, like I love playing chess. Everyone is interested.
Hi everyone, my name is Raman. I also work at Geospatial Analytics as data scientist. So I am with Santosh and Tyaku. There are 4 people who organize this meetup.
Hi everyone, I am Amrit Kiran. I am a senior researcher at the Indian Institute for Living Settlements in Sadashinagar. My work mostly runs around spatial data infrastructures, visualization, big data, continental data analysis and all that. But yeah, I've been there for about 5 years now. I joined as an intern right out of college from the Indian Institute of Remote Sensing in Leaveraging. But yeah, so the background in a lot of programming, a lot of GIS. It's been a while since I've seen Python, so thanks Krishna for that. I think refresh my memories on how I forgot about all this. But yeah, so yes, that's about it. Also, just a small shameless plug. At IHS, we have the Urban Writings Festival. It's open for the public, so if you're interested in events happening about the city in IHS, you can just walk into IHS today and tomorrow. A lot of exhibitions, a lot of panel discussions, very exciting. So yeah, so just walk in. There are beautiful exhibitions. Very interesting one is it's called Vasane. I don't know if you know Kannada. Vasane means smell. So there's an exhibition where you have like a bowl and you have to smell it, and you have to sort of remember what the smell is. And it's the smells of the city. So it could be like flowers from Kaban Park or things like that. You have to guess what the smell is. It's pretty interesting. If you're around Sadashiv today and tomorrow, please drop by. So I just want to say that. Cool. Thanks all. We can start with our next speaker, Adithya.
Yeah.
I think I'll have a small introduction. All you maybe a little bit.
I think he can use it. He can toggle it.
That's his presentation.
Yes. Can you just change the slide for him? Yeah, you just have to connect it.
I'll give the intro as we are setting things up. So yeah, so next speaker is Adithya. He's a co-founder and chief of product from SkyServe AI. With the mission planning, space system architecture and systems engineering career, Adithya previously led the team in this Axiom Research Labs missions operations. And with a background in aeronautics, astronautics and space engineering from the University of Petroleum and Energy Studies and Cranfield University, Adithya co-founded SkyServe AI in 2020 and is the chief of product dealing with geospatial intelligence, product development, management and placement. Adithya is also a recipient of the NASA Systems Engineering Award, where his team at UPES won the best application of project and risk management practices in the design and fabrication of an aircraft for the SAE Aero Design Best competition. Adithya will be presenting leveraging edge computing for Earth observation today. So if you all welcome him with this one round of applause.
You can just say it, then switch.
Hello.
Can
you hear me?
Yes.
Hello, mic check.
Yes.
Yeah, maybe a little bit. Could you center? Okay. Oh, okay. Cool. Yeah, so just to introduce about what our company does, and I think probably it fits very closely to the theme itself, that it's an emerging trend. And especially looking at edge computing, it's probably in the last 3 to 5 years, it's been coming up on the earth. So a lot of IoT companies have slowly started seeing that you can't just send stuff in a factory and send all that data back to the data center because the amount of data is huge. And plus you have disruptions in communications. Just in India, you can imagine that, say you're putting sensors in Pina and your headquarters is in M0, and these cables are always susceptible to our municipal government digging up the roads, and you could just lose all the data. And these IoT sensors have generally been a little low-tech, so which means they're just collecting information and sending it across. They don't even have storage, and forget about any amount of computing to compress the data, or maybe to cache the data, so that you can't communicate back to the data center, then you can at least save some amount of information is still there. So the paradigm of bringing some compute closer to the sensor started there in most of this industrial IoT setting. And slowly those concepts have started getting recast in different industries. So slowly this has started coming in industries where there's a lot of danger to humans, so you can't keep sending them to sense or to check the integrity of some machinery. You probably can't. So one big example is, say, oil rigs. A lot of the inspections were previously being done by expert divers who would go closer to the wellhead and try and see everything is good or not. Then they started sending robotic submarines. But then over time, what they realized is just put sensors there and they will tell you all the full picture will come there. But then again, this is similar to an IoT sensor. This is connected to some sort of information grid. But in case the communication is lost, what do you do? Can you put a little bit of compute there? Can it compress data? Can it also tell when there is no incident, don't send data, so you don't use power? So many of these are fit with small battery packs such that they can be remotely installed in different places. Maybe they can even communicate remotely through like wireless radio or something. But they can't keep sending data. So you need to conserve this. So some amount of computing just to tell that prioritized data package is the same. So all these are ways in which edge computing has been permeating into all the sort of industrial sectors. And we've looked at taking that, putting it into space. It's not completely new. Maybe it's one of the, I think, early starts across the world of using this technology in satellites. What we're focusing specifically is to how to bring that into Earth observation and how to bring benefits of this technology to all the people, all the way from the companies that are building satellites, or probably agencies that are building satellites, all the way to the people who are consuming the final information. So it's like, just to compare how it works in the current scheme of things. So you have satellites that are imaging the Earth. They send data down to something that we call as a ground station, so basically an antenna receiving all these signals from the satellite. They basically have a massive database either on their premises or on the cloud today, as a lot of companies are using the three big cloud providers' infrastructure to store all of that data. And depending on the resolution of this satellite, so say it's a 30 centimeter imaging satellite, and maybe you have like 5 or 6 satellites, you can imagine how much data would come into. There are some companies that are actually accumulating 2 to 3 terabytes of data each day. So that's the amount of data just coming in, and all that data is not really usable by people. So there's a lot of processing that is done to discard unusable data, faulty data, and at times data that nobody wants. So they basically archive it, compress it in so that they can save on cloud expenses. So say you have an optical image with clouds in it, and that cloudy data really doesn't sell. So they'll archive it and use lesser space on the on say a S3 bucket or something like that on archive. Costs less, but also to fetch it, it would take more time. So if somebody wants instant delivery, they can get instant delivery of readily usable data. But somebody who really wants to look at the shape of a cloud, maybe they're working in climatology or something like that, or meteorology, and they want that information, but those number of people interested in that is less. So that sort of filters out all the data that's been captured by the satellite, bringing that down to probably 2 images from one particular orbit of the satellite around the Earth, and those 2 images are now available for anybody to buy. And let's look at it from the other side. So say you have a company or an institute wanting to do some studies, and they want information. So say they're looking to predict yield of a particular crop in a growing season, and they go to some consultant, or they go to a company that actually does geospatial analytics, and they tell them we want to solve this problem and we need to do it at scale. Do whatever is required, here's my budget. Now with that information, say an analytics provider would look at the catalog of data that's available, try and match the problem with the solution, and the solution will not just include buying data, it also involves applying certain models. Some of them say could be unsupervised, like Krishna mentioned, and that is something that they bring their subject matter knowledge. but they need data as well, because you need the latest observation of, say, fields of interest. Now, they place an order to, say, some sort of aggregator or person who sells satellite data from multiple satellites, and they go and finally buy one image. So, probably thousands of square kilometers were imaged. They were filtered out. Maybe you have now 1,000 square kilometers of sellable data, and out of that somebody buys like one image, maybe it's like 10 by 10 kilometers. Now you can see here what happens is on a need basis, like even if you map multiple users, you still have a lot of data captured here which will not get used. And this is inherently the problem with any large scale imaging solution like satellites. They can observe the whole Earth, and there's always the risk that if you were to turn off the satellite and say, I want to save money, I don't want to send down data, what if at that moment you could have imaged the place and that image somebody would have wanted to buy? So just be safe, spend the money upfront, get the data down, and hope that more of it gets sold. So the whole paradigm that is there is more expensive, it's less efficient, and many a time what happens is user needs are never really taken into consideration. So if it was that the user had a requirement, they could send up the request all the way to the satellite guy to take an image, and the image was taken and only that was delivered back, it would be great. This paradigm exists, it's called tasking, and it's a really expensive journey that companies take today. And they do it only if there's no other way to do it. So there are some companies like Planet which take an image of all of the landmass on Earth every day at 3-meter resolution and make it available. So you don't really need to ask anything, but they're doing this inefficiently. This includes images of clouds, it includes images that are blurry, which they themselves delete well before in this filtering process. So if you bring edge computing, and this is again more of a ideal that we at SkySo are trying to go towards, is take some of this logic and try and put it onto the satellite. So here you know what are the criteria for an image to be useful. You know what are the failure criteria, say if it is blurry. A lot of computer vision folks know how to detect blur. Certain types of blur, if it's motion blur, Gaussian blur, you can figure these out. Say there is lens glare, you can also detect that. And there's a lot of training being done even on the ground to reject that, sometimes even to correct such sort of artifacts. So you can take that and put that on the satellite. Next comes the subject matter knowledge, which basically is creating a model that can get the inference or insight from the data. So that is known. So they are responding to user needs, but essentially these models exist. And what if you were to be able to bring them all the way into the satellite? So now if you're able to marry both of these capabilities on the satellite, and what basically happens is even if you're taking images which still have to be done, you can filter them out, and whichever images meet the need and they coincide with the locations of the user's interest, run the model right on that image, and if the result is say a spectral index, or it could be an object detection output, it could be segmentation output, you're basically reducing the dimensionality of the data, effectively reducing the size of the files that you're sending down, and that is the biggest operational recurring cost for all these satellite based, which influences the cost of data. So it's very hard for anybody, maybe in the institutes, to think that I want to do mapping of Karnataka on a monthly basis at 30 centimeter resolution. It's unheard of. Nobody ever thinks of doing it. Nobody will pay you for that. No budget ever gets allocated for doing that. But if you were to do that on the edge, I think it's far more possible, and I'll just show some examples of how that could be done. So essentially what we're building towards is communication, especially for those who need to extract just information. They're not looking at a mapping problem. What you can do is you're just having machine communication. You have an API that is called based on some front end which a user can understand. You're calling it to define a particular time frame, a location, run this model A, model B, and run it only if the image is clear of clouds, or probably the look angle is correct, or say in terms of soil interferometry, if you can get a baseline of X, Y, whatever that is, then run this sort of analysis to see is there any change, is there, probably want to calculate the height of some object. So you can do all of that based on rules, and those rules will be managed here rather than bringing the raw calculator. Yeah, so that's the overview of what we're trying to do and sort of changing the paradigm in the way we operate. So it's, if you were to look at it from like just the previous conversation that we had, is if you're exploring how to work with data, you really need the data with you first. But once you know what to do with it, and probably know the discrete steps that are required to convert that image data into actionable information and integrate that probably into product or a dashboard, you could literally just take that logic and push it all the way up to where the data has been created, and then now you're only getting that, and this is very, very scalable. Yeah, so this is a little bit of math, and basically helps appreciate what's being done by the satellite developers. I think from Galaxy, I think that's basically a big problem that everybody deals with when you're building the satellite, is the size of data. And just for those who are doing applications on the ground, it's interesting to see how and where this data is getting generated from, and how that is actually impacting us. There are many times we actually just ask, why is it so expensive? This is the reason it is. So imagine you're looking at so modified the information here, so not specifically representing any one company's sensor. So this is a hypothetical imaging sensor, and each of these strips captures light in a different wavelength. So imagine it is maybe red, green, blue, and near infrared. Let's just think that, and the product that comes up is a 2-meter GSD image, and if you map this on the surface of the Earth, basically the width would be 13 kilometers, and every image, like say what you're seeing here, the vertical height would be like 9 kilometers, and as it is scanning, each of these, basically the screen would start like this, and then slowly all these 9 kilometers would be covered by green. Same way, this would start from here, and then so basically till you reach the topmost 1/4, the top quarter, you don't have complete data on all the bands. So basically this is just one band information if you keep sweeping. Here you have 2 band information, 3 band, 4 band. So you need to do this because the imager can't work partially, right? So as it sweeps across, you're anyway generating waste. And this waste is significant if you look at it at a large scale. So just look at this. So you're having 4,500 pixels divided into 4, each one is roughly 1,000 pixels. And 1,000 pixels into 6,000. So much data is there which you could discard, just as an idea. So if you were to look at this one raw frame, like just one capture, take an image and just see what is the size, it would be roughly like 44 megabytes. And in that 44 megabytes, we are seeing 3/4 of it is actually not useful, but it will still come down to the ground because satellites today can't really do anything about it. They have to just bring it down. So if you're looking at 3/4, basically would be bringing down maybe 10 megabytes if you were somehow able to figure out that this is the portion that you have to chop. And a lot of compression algorithms have come over time to basically reduce the size of the data, spend less to transmit data. It's essentially a communications sort of a business, right? Where ground station guys just install this in really high elevation places where they can see the full sky with least amount of interference from civilization. And at that point, they need to recover the cost of the property that they've paid for. So they're going to charge you on a per minute basis to pay for data that is coming down. So every minute saved is literally money saved, and this you scale it across 365 days in a year, how many years the satellite is operating. So much money can be saved. And that will translate ultimately to the user paying for an image. So compression algorithms have come in to try and do that, But you can see here, you're reducing max probably by 2.5 times, and it's still there. It's still significant. And now you scale that, say, for an imaging pass of 100 kilometers, maybe one district could be sort of strip mapped by maybe 4 or 5 of these strips, a small enough district. Now that pass results, so just some more calculations, basically it comes up to something like 800 megabytes. This one strip of 4 bands with say 12-bit representation for each pixel comes up to this. This is compressed data. Now when this comes back down to the ground, you say do a unzip or a deflate or something like that, and you're close to 2.5 gigabytes after registering the product on the map. So basically you have georeferencing information, all the bands are setting nicely, so each pixel is basically looking at the same region on the earth, and you have all the 4 bands. And the limitation of today's computers is that you can't just represent 12-bit data somehow, so they need to go into some sort of right-aligned format. So there itself you end up adding some more inefficiency, and 12-bit data is represented as 16 bits, so it goes from like 2 GB to 160. Now this is the raw scene. Many companies will never sell you a full scene. They will split that into tiles and have some sort of cool pricing strategy around that, which will cover a lot of this inefficiency. It will also cover data hosting charges, because like just what we saw it in QGIS, you're getting this in terms of tiles. So those tiles typically they sell in terms of like 5 kilometer by 5 kilometer tiles, and then that is a 50 MB file. So you're buying in units of 50 MB, which originated basically like this. If it starts off as 800 megabytes, you're buying in units of 50 megabytes. This is basically the process in which the product that you're purchasing or downloading on the earth has been created. Yeah, next slide. Yeah, so now putting this into a user perspective. So say somebody wants to monitor encroachments along a pipeline, and they have gone to an analytics company and they have recommended use satellites because you have a very long stretch of pipeline, probably cross-country pipeline. Say just in India you have like 15,000 kilometers of WTS pipeline. And monitoring that basically today has been done by people. And people walk across the length, one person doesn't walk, there are multiple teams deployed, and they, on average, they will complete the full walk of 15,000 in a month. Combination of vehicles, combination of drones probably, and people. They'll complete this. So once a month they get to know what is the state of this in case there's anybody trying to go poke a hole in the pipeline and steal some of the fluids and sell it somewhere locally, or they just want it for cooking gas. I do not know whether you can use the LPG that comes from there for that, but there are people who are actually trying to pilfer these fluids, and it's very, very common where you have a lot of habitation. Because they see a free resource there, all you have to do is do something that is illegal, but it's easy, it's accessible. And they will usually not do it when everybody is seeing. So if somebody is coming for inspection, these guys will cover the ground if it's an underground pipeline and just walk away. You will not be able to see it, but you need to see it when they can't see you seeing it. And drones have a drawback because you can see the drone. Maybe it will even give you like that nice rotor sound that hey, okay, it's coming there. And nowadays people have come up with like just throwing the stones and stuff like that to attack the drone. But satellites, especially the guys who are doing this pilferage, they do not go on some fancy defense website and try to say, okay, where are all the satellites today? Okay, I will plan my crime at this time. So they're generally not like that. So you can use satellite data for that, but the key problem is based on the indicators that you're looking for, maybe the resolution of images is not like a Sentinel-2, or you can't, as in Sentinel-1, may not be able to pick up what you're looking for. So maybe you need higher resolution, and that's when they end up having to create a budget for this. And this is again more. For an example, this may not be the actual methodology. So acquire satellite data along the pipeline once a month. So you're basically benchmarking against how humans are doing this, walking across the length of the pipeline. Apply a sequence of change detection and object detection algorithms. Mainly there are more processes that may be involved. Then localize and characterize incident. So basically find the lat long where this is happening. So if you had to act on it, you can send a team to go look at that place. And it would be helpful to characterize these incidents into probably one of these four, based on which you can alert a related government agency maybe. Or probably if you see damage of the pipeline, maybe you can send the team to go fix it as well. Not that you send an inspection team and, oh, now we need to fix it. Okay, now we need to bring down the whole pipeline, bring the team in, maybe after a tendering process. These things happen. Tendering process is happening when fluid is leaking out. And then they actually take this, okay, let us shut off the whole pipeline and then wait for this team to come in and fix it. So, and the ultimate thing, of course, is all this is to take corrective action. So either you can install more guards based on what you're seeing as a pattern of life, or probably you can again go reactive and fix it. But the key thing that you're seeing is this is being done once a month purely because the customer probably only understands that this is usually done once in a month. And just for meeting this requirement, the cost of satellite data, so say some of you may know the rate card, but I'm just putting variable P per square kilometer, and for a 100 kilometer stretch for 12 months is 1200 times P. And there's this obvious part, hidden cost why P, is that the satellites probably have to fly above the place more than once, especially for optical, to guarantee that there's at least one image that they can sell the customer. Otherwise, if they just flew above it once, they could not capture that location, either because of cloud cover or bad quality imaging. They have to give money back to the customer. The customer actually paid upfront. They have to give it back, and this is not a great situation if you're trying to run a product. So, yeah, so just keep this in mind. I'll come back to this. Yeah, next slide. So, again, this is going towards the ideal of how edge computing could be used. So, satellite takes an image. This is basically one scene. Basically, after doing some of that pre-processing on board, you achieve that scene. And your area of interest is basically this patch. You run your change detection and object detection, and what that requires again is you have a pass above this place, say on some date, and when you fly above that place again, you register both these areas of interest with each other, try to find the change. So you could do that through a variety of ways. I will not get into that, but outcome could be basically finding some encroachment. There's some sort of a dwelling that is turned up here. I don't know if it's visible. So basically, this region did not have this building. It's basically a caravan, sort of portable cabin that can be brought in through a trailer and just kept here. And that's there. This is clearly not great because this is the right of way passage which this pipeline operator has, and they're not supposed to have any such things happening. So that detection can be translated into a GeoJSON. So you can basically have the feature type, the coordinates, and probably if you're having some sort of object classification, you could bring even that, like just put the class label. Now, if you wanted proof and you're basically just extracting one region of interest around this incident, even if you just take that of some half kilometer by half kilometer, this image is all that you need, and it can be highly compressed because you've already made the inference. This is only for context. It is telling you, I detected a building and this is how it looks. You could even just send this as a JPEG or PNG image all the way down to the ground. And over time, maybe people don't even need this context image if the models start getting better. It's possible that the models have to keep getting improved over time. So probably once in a while you can get these images. But you're seeing that the raw data strip, which was used to construct a scene from which you could take a 50 MB type, and from there localize the change into half kilometer area. And finally, all you wanted is just this piece of it. This is all they were paying you for. And this is essentially like roughly 100 characters, fitting that into particular type of data type. Probably it is like 2 bytes per character, and that's maximum 250 bytes. Massive reduction, and all this is only getting generated when there's a change. If there's no change, probably you're going to have one character saying 0 or no. So this is the ideal towards which as an edge computing across the world is working, and they're trying to bring, basically deliver that every time the satellite flies above that, it will do a determination and send this output. So yeah, so what you saw here, right? So 1200 times speed. Now that 200 byte size information is almost a millionth of that 50 MB type. Both can do the same job. One costs more. One has data flowing through ground antennas, through data centers, probably even doing on-prem processing. A lot of places this data goes, but essentially the requirement is just that piece of information, which is just that JSON text that we saw. And even if we assume that nobody is going to sell you that information at 1 millionth, and somebody will realize that this is valuable to a customer, they will not sell it like really so cheap. Say 1/100th of the, like, just to be clear that somebody wants to make money out of this. Some sort of unit economics forces them to sell this at 1/100th of P. So say if P is maybe 1000 rupees, this is 10 rupees. And this allows basically the user to spend less for the same frequency once in a month, or same budget, anyway they have to spend it on that. Theoretically they could do the same inspection 100 times. So 100 times a month probably is not great, maybe 10 times a month is good. Every third day you're getting an update that, okay, the full pipeline is clear, no incidents, okay, here are the places where the incidents are. You could even start seeing which days of the week are people doing stuff around your pipeline. So this basically is the vision, the theory, the advantages, and on next slide. So basically, I have if you could move, yeah. So this is not great color choice for me. So this is basically our test edge computer. So we focus on the software that runs on a computer that can be put on a satellite. But some satellites today don't have that sort of horsepower to do that. So we built one of our own. This will be flying 2 or 3 times in the coming few months. So this is capable of just taking those raw frames which have those multi-band information, correct them radiometrically, say for sensor noise, defects in the sensor, even if the sensor degrades over time, because this is in a very dangerous environment where there's lots of radiation hitting the sensor. Sometimes pixel will just go blank, or it might always give like complete high value, like saturated values. So it sort of will start looking like there's lightning hitting or something. So we can correct all of that on the satellite, and after that stitch, say in that case it's a 4-band scene with all the bands nicely stacked. Here, next slide. And taking that, if there's any atmospheric effects, we can compensate for that as well. So you reveal more of the scene. So if it is thin haze, probably thin transparent clouds, you can remove them. Some enhancement will be there, but based on what the user is doing, suppose you're doing object detection, it will work. If you're doing spectral indices, maybe not. Maybe you don't want to touch the spectral values. And then, say you want to run a cloud or cloud shadow segmentation mask to remove some parts of the scene from your calculation, and then we georeference the scene ultimately, so that now your area of interest can be found, and you can run your algorithm or model only on those pixels of interest. So that's ultimately what we do. We bring that raw data all the way here, and then now we hand it over to any of these geospatial developers to put in their application, exploit this, and then deliver to their customers or deliver on a project, or even say do some sort of large scale analysis, because it's now more feasible and sustainable. Yeah. So, yeah. Again, yeah, everything is dark. So our company's color theme is basically dark blue and yellow. So yellow is seen with dark blues. Okay. So basically, this is what we are building to exploit this capability. So now you put compute capability in space. Somebody has to exploit it. So how do you exploit it? We're building basically an automation pipeline with some tools for folks to build an application. Probably you could have already built it, tested it on the cloud. You're maybe even delivering projects and results using that. But now we're enabling you to bring that, push it into the pipeline such that it will validate your model and is it ready to run on our device, on our the types of sensors that we're flying with. And once that is done, you're basically ready to push this to a satellite that's currently flying, which can support this sort of software, or any new satellite on which this capability is being put. So continuously improve and basically evolve the model based on the business needs. That's also possible because it is now software. You can just upload it all the way into the satellite. And so down the line, this is more of future work. So we want to provide a way to track how your model is performing. So, and in case it's been throwing errors, it's not really giving the inferences that you want, and you're able to validate that, let's say, sample input images on the ground. You can start taking some more data to train. We're also going to build some simulation tools such that you can create data sets which are self-labeled. So there's a lot of work going towards creating synthetic data, which is going to basically bring down the time to create new models. So that is something that we're looking to integrate over time. Yeah, thanks. Oh yeah, that's what I had to say.
Yeah, time for some questions.
So I'm just wondering, if we're moving backwards from the detection part, how quick is the satellite going to capture the image? So let's say the pipeline example that you gave me, like let's say it's detected a leak or someone's like trying to steal something from it. So how quick would the satellite be able to detect that there's a leak and take that image and be able to capture the...
Yeah, so this is based on how many satellites you have. So typically a satellite, in most of these orbits in which they're being put, they probably would take roughly 20 days to fly above the same place.
Okay.
So what they do is space the satellites in orbit in such a way that they can fly over the same place within probably 2 days, 3 days, and things like that. So today there's one constellation of satellites which I think almost has a 6-hour repeat frequency.
Okay.
And those are being used for basically monitoring the plane.
Okay, thank you. And one more thing, sorry, does SkyServe already have your own satellites that you're able to capture this image and deliver?
Yeah, so consciously we stayed away from building the big thing. So we're focusing on just this part, which is just build the computer, if the computer is already not there on satellites. But if it is there, we just provide the software and link that software all the way to the ground. So our key focus is actually build everything as APIs. We are today building a very basic front end, but essentially the users will build their products on top of this. So that's our intention, that you're able to leverage some satellite flying somewhere to get your answer, and you really don't need to know much about that. So basically you do your product development as you do any product, but the information feed that you need is basically what you're doing.
So the more satellites you work with, the quicker your data.
Correct. That's basically been what we're doing.
So I have one question. You can go back a couple of slides if that's possible. No?
Yeah.
Can you go back? The calculation. This one. Next one. Yeah. So here you talked about that. Okay, not the previous one again. The slide where you showed that 50 MB was the initial and you got it down to 1 MB.
Yeah. Just go back. This one?
Yeah, I think. So you showed that initial tile size is 50 MB, and when you process it and you get only the GeoJSON, it's 1 MB and you downlink it. So my question to you is, assume that you have a communication system which has around 400 megabits per second bandwidth, which is 50 megabits per second only, very much feasible. It will take 1 second to downlink all this data, right? And at about 60 watt of power, if it consumes 60 watt of power, 60 watt seconds is the energy that I'll spend, right? Now, essentially when you're putting up a computer on the satellite, right, it's going to take its own computation time and computation power, right? The energy that it is you're spending, right, should be significantly less, right? Because it should be significantly less than that 60 watt seconds. Otherwise, it will just be more efficient for me to communicate all that data to the ground than to process it, right?
Perfect. Yeah. So as of today, in fact, that's basically been the growth of edge computing. So what they've been able to see is you can compute certain types of data today based on the algorithms, best-in-class algorithms that are there, which are efficiently using memory, efficiently using processor threads, to bring that net energy at least on par, if not better than the transmit capability. But the key difference actually here is that if you didn't have to communicate it down, that is a great use case. So today the base use of this is just to filter out data so that you're not, so say you're making some like 10 collects like this in a day, or probably it's too less, but say in an orbit you're doing 10 collects like this, and you could eliminate one such collect just based on onboard processing. So you're reducing some amount of data that you're bringing down, because ultimately nobody needs it. So it's like that sort of hoarding mentality most of the satellites have today is we need all of it, because never know who is going to. So that mindset change is also something that is a barrier today, which is even if it makes sense that power balance and energy you're able to calculate that and figure out for this use case it makes sense. Maybe for this use case it doesn't make sense. You have to get all the data down.
Right. So I'll give you a satellite data perspective, right? You say that satellite wants to hoard all this data. That's not right. Nobody wants to do that, right? But for satellites, the energy that you have to capture the data, right, is of prime importance, right? So unless this approach for a satellite provider, unless this approach helps them to kind of, be energy efficient, right? Because if I have to spend more energy, right, to reduce the data, and that in turn is limiting me to capture more data for more people.
Yeah, that's what I'm trying to say, that the use cases today have to be realistic enough that they match the technology also of today. So today, we've done this for some of the satellite partners that we have, where we've seen, okay, the power that we're using and the time that we're doing all of this thing is certainly more efficient for this use case compared to them transmitting. So those guys have tried to bring down their cost by reducing the data rate on their transmitter. So net, and most of those transmitters that if you're trying to save money, they're not really that efficient. So probably you have like a 30% efficiency on those radios. So clearly there it made sense. Now you start going for bigger and bigger satellites. Now the power available is greater. So what I would do, I would take a more powerful GPU or a FPGA such that I can do the compute in basically one spike and get the work done, such that I'm not transmitting. So because you actually have peak power available when you're in sunlight, you can make use of that. But it's purely based on what is that use case. So if you're trying to reduce data, yes. If you're trying to do that full inference, right, that would certainly take more time, more resources. So then you have to compute for that case. So there, can I do all the steps, or can I stop somewhere in the middle? Maybe I can just crop out that area of interest and only send that down. Maybe that's more efficient, because maybe that CNN model ends up taking a lot of time to do the inference, so I just knock that off the pipeline. So
we'll discuss it later, but I think one more suggestion. In your initial slide when you were showing the whole processing chain, right, there is one very critical step in optical, especially for optical processing, which is atmospheric correction, right? And atmospheric correction models usually rely on data from satellites like bodies, which have these spectrometers that capture atmospheric data, right? Now, if you really want to do something like a vegetation growth analysis on the satellite, right, you need surface reflectance, right? So I think that is something you need to think on, because it's going to pose challenges.
Correct. So right now, again, the efforts that we've done so far is to be able to deliver a top of atmosphere product. So now going to surface reflectance clearly has that. We've done some work on that, but again, this is where I give a disclaimer. If you're using any radiometric indices, don't do that now. You can do more feature-based stuff, but for radiometric indices, that will take some more time, because the way of modeling this problem is slightly different. And we'll have to see how we can do that. So probably one way is upload calibration lookup files, as in some software on the ground already does this. So, but that has been built on the predictability of atmosphere with seasons. And we're clearly seeing that is no more valid. Every year, the cloud cover in a particular place is like not even matching that particular model. So if you're taking the lookup table saying June, July above India, it is going to be rainy and cloudy, great. But what if it is not? What if you have late monsoon? It's sort of dry, the air is sort of thinner, and I have overcompensated my atmospheric correction. So many of these things are evaluated a few, and basically what we took the decision is we will not accept anything that wants real spectral values. Anything that is creating a feature on top of that and it is robust to this atmosphere, great. But yeah, over time we have to solve the problem.
Also, really add to the frustration, it's probably not just about the power efficiency, but also about the ground station availability. You have only so much downlink possible, so might as well send the most valuable data than sending the cloudy data. So if we extract as much information as possible.
No, that's right. But let's say in one pass, if I capture the data and I spend all my energy processing it and then I'm downlinking the insights, I'm not using the bandwidth available. So one case, I'm capturing so much data that the bandwidth available is not limited.
No, I understood your point. But considering the satellite frequency and the resolution below Earth, the satellites that are coming, it's not possible to send all of that data.
It's true.
So just send the.
No, but I think that's more of a suggestion that that
this is also something that everybody needs to keep thinking. That is, actually there are some cases of when we speak to folks in ISRO today, they are capturing data for mapping, and they've told even if there are clouds, this is useful. There's one team that only wants to look at clouds. Great, yeah. So edge computing really doesn't contribute much there.
Let me put it this way. I think the distinction is that when you are speaking, you are having archiving in your mind, but I am having tasking in my mind. So when you are actually doing archiving, if the satellite provider can still archive while reducing the data, I think it's a huge benefit, right? But for tasking, it's a different.
Actually, tasking is actually the place where we are seeing the most uses, because if the task's outcome is fail, basically I have not covered the area of interest because of any reason, natural phenomenon or satellite error constability. You can cancel that spend on your side. So basically, say 2 downlinks and 1 cell. 2 downlinks is 2x, but you are charging probably 2x plus small delta x to be having some sort of a margin. Now that 2x is the basis of your pricing because you have to factor this. So if you can make 2x as x, great, you can still charge 2x plus delta x, and you're actually closer to making this sustainable. So that's an idea that we need to try and figure out how to do that. It will require a lot more factors.
No, see, what I was suggesting is you have that calculation because that will help you showcase your value to a satellite provider.
Yeah, this is all just case studies.
Yeah.
So again, some secret sauce that you can call us if you need consulting. So,
thank you, Adithya. Last time I met Adithya and Vinay was at that IEEE versus AGM meeting, and when they told me that you could do all of this on a satellite, it just blew my mind. Like as a user, as a developer, as a researcher, whatever, this was not in my frame of view at all. So things like this, when it comes up, it's just like cutting and cleaning and stuff. Pretty cool to see that it is picking up pace, and I'm sure there are many. It's just that users side they don't know about all of this. So I'm sure there's a lot of, let's say, mind-changing perspective changes that you have to do before all of this sort of comes in.
This will take time for anybody to think how to use it. That's the reason. Right now we are thinking how to build it.
Yeah. Thank you so much. So our next speaker, Rakshit, he is the co-founder and VP, product at Leaveraging Space. Rakshit is an alumnus of IIT Madras with a bachelor's in engineering design and currently serves as a vice president of product development at Leaveraging Space.
having played an integral role in building the renowned team Avishkar Hyperloop and his background in AI research at Siemens, he led the efforts at Galaxy to build products that combine AI with satellite imagery deployed on the edge and cloud to deliver the best possible insights about our planet. His goal is to make a meaningful impact on our planet and society through the use of cutting-edge satellite data. Rakshit will be presenting the power of data fusion, optical plus SAR. A small round of applause.
Oh yeah. I've shared on mail.
So I hope that everyone is still very energetic, given that we have had 2 really intense sessions. Come on guys, a little energy please. Are you waiting for tea?
There are refreshments that if anybody wants. Yes.
Not necessary that you take after, no, it's a take.
Yeah.
It's just downloading. If anyone wants to get tea or take the bathroom is downstairs.
Like, do you guys want to take like a 2-minute quick break and then kickstart things?
Sure.
Yeah, sure. Let's start at 12:15. Just 5 minutes left. So.
Put the volume up a bit. Push it to the thing.
Hello. Check. So I kind of changed the title of my presentation a little bit to make it a little more exciting, right? So how many of you here are familiar with generative AI? How many of you have used ChatGPT at least once till now?
Use it to write your introduction.
Definitely. Right. Yeah, so generative AI is kind of the broader umbrella under which ChatGPT is kind of one of the models. So it's kind of recently generative AI has picked up and skyrocketed because especially in language modeling there have been a few interesting use cases and a few exciting discoveries or in kind of like inventions like the transformer neural network, right, which turned out to be pretty accurate in some of the tasks. But there are other avenues of research, where you can use these generative AI models to do really cool and exciting stuff. And I think fusion of satellite imagery is one such avenue. Although it's very tricky and very challenging to use some of these models. But what I want to do in this session is I want to expose you to some of these use cases, right, where generative AI is kind of relevant in satellite image fusion. And I kind of want to give a little bit of introduction about what generative AI is, how can you get a feel of it, right, and then we'll deep dive into some of these use cases, where this is relevant, why this is relevant, and how can you kind of pick up this domain and then, start churning out some results. Thanks. I think, the introduction has already been done, so we can move past this. Right, so the outline of the talk, a little brief intro to what exactly are generative AI models, then few use cases where these are relevant in the context of fusing satellite imagery, and then finally some closing remarks. Right. So I think on the right you see one of the outputs generated by the software called as Dolly, right, which is text to image generation software where you can just give any prompt to it and it will generate an image out of it, right. So basically, broadly categorizing it, there are 3 different type of generative AI models, which are being used. First, and I think very popular ones are generative adversarial networks. A few years back, the research in generative adversarial networks kind of took off, but since then it has been saturated because there have been no exciting discoveries here. Transformer-based models, again, because of some of the use cases which we have figured out where they perform brilliantly, right? People have built extremely popular and extremely well-packaged products out of it. The third one is auto-regressive convolutional neural network. These are kind of still unknown to a lot of people. They are used mainly in applications, which deals with time series data, like predicting stock market prices, fluctuations, all those things. Right? So the most relevant for us, since we are dealing with imagery domain, are the generative adversarial networks. And in this talk, we mostly cover the generative adversarial networks. Yeah. So what exactly is a generative adversarial network, right? So a good way to understand is, so let's say there is a judge. So let's say you participate in a drawing contest, right? And there is a judge who judges your drawing, and based on that judgment, he gives you some sort of a reward, right? And let's say you make a drawing which is extremely bad, extremely horrible, from some random thoughts that were there in your mind, right? And this judge kind of told you that this is horrible, you get a 0, right? You will go back, you will kind of retrospect what went wrong, and you will try to come up with a better drawing so that you can get more marks, right? And this process will keep going on for, let's say, 1,000,000 times till you become an extremely good artist, like Da Vinci or something, and you create a Mona Lisa, and the judge is kind of compelled to give you a 10 because he can't differentiate whether you are an amateur artist or a extremely talented artist, right? So that's kind of the fundamentals of how generative adversarial networks also work, right? So there is a generator. Wrong choice of colors. But there is a generator, and what the generator does is it takes some random noise, right? And then it produces an output. So let's take a simple task that I want to generate faces. I want to generate random faces, right? Which probably do not even exist in the world. So what I do is I take some random noise, I'll feed it into the generator, and it will give me some output. This will certainly not be a face at all. It will be some random garbage, right? So what I'm going to have is a discriminator, right? So the discriminator is like my teacher who is judging my artwork. What my discriminator is going to have is access to how actual faces look like, which is the data that I'm going to have as my ground truth data, right? And what my discriminator is going to do is going to see that the painting or the art that you have presented to him versus how actual Mona Lisa looks like, and then it's going to rate you a 0 or a 10. Right? And this process is probably going to repeat, let's say, 1,000,000 times till the generator network actually learns to produce images which the discriminator can't discriminate from the actual ground truth data. Right? And the beauty of GANs is in the mathematics of it. Right? I've just written one loss function which I'm just going to give it a shot to explain to everyone what it does, right? So this is actually a min-max optimization problem, heavy words, but what the generator is trying to do, it's trying to minimize this equation, right? So if you focus on this part of the loss function, right? If I have to minimize this part, right? My log of 1 minus d of g of x should actually, this value should be closer to 0, right? Because log between 0 and 1 towards 0 it tends to minus infinity, right? So if I have to minimize this, 1 minus dg of x should tend to 0. That means dg of x should go to 1, which essentially means that my generator is trying to fool the discriminator, right? So discriminator will label 1 if it's a real and 0 if it's a fake. Right? So if, and G of Z is the output which is generated by my generator. Right? So if my discriminator labels the output generated by my generator as 1, which means it has fooled the discriminator. So what the generator is doing, it's trying to fool the discriminator. Right? What the discriminator is doing, it's trying to maximize this equation. Right? So if you now focus on this part of the equation, X is my ground truth data. Right? And if I have to maximize this needs to be closer to 1. Right? Which means that my discriminator has to label 1 for the ground truth samples. Did everyone got? Is everyone with me? Right?
Is it like we keep fooling the discriminator to keep generating more data to make it better? Is that what you're trying?
Right. So generator is trying to fool the discriminator.
Okay.
Right? And the discriminator, it's a good callback.
Yeah.
Right? Generator is trying to fool the discriminator and discriminator is trying to kind of, cope against it. Right? By learning from the ground truth data. So this is basically kind of the vanilla GAN network. Can you click on this link? I have a very, very simple visualization to show you how actually this thing works. Can you click on this link?
Yeah, he's clicking.
Shift click or
Control click. Just exit and then click.
Right. So exactly what I was saying. So what we have here, so basically every stochastic process, like any data which is generated by any stochastic process, usually comes from an underlying data distribution, right? So let's say this is the data distribution, underlying data distribution from which I am sampling my faces, right? It kind of looks like a Gaussian, I don't know. Right? And as of now, as of 0th epoch, I am feeding some noise to my generator, and what it's generating in turn is some noise. And my discriminator is trying to predict whether this is real or fake, right? So what ultimately I want my generator to do is to produce samples that look like this, right? So let's see what happens when you train this. Can you push the play button down? Yeah, so as you see, as this process continues, right, the generator starts to generate samples which will look very close to the data distribution of the real samples. Yeah, it's already started to converge. Right, so if you'll probably leave it for like 10,000 epochs, it will be able to generate samples that look exactly like the real one. So everyone got the underlying gist of how these adversarial networks work? Can you go back? Yeah, nice. Right, so probably the first use case of these generative adversarial networks, right? I first answer the why of it, right? Why am I even talking about this, right? So, how many of you have seen a synthetic aperture radar image once in your life? Okay, great. So I think the ones who have seen just support me on this. It looks horrible, right? It's very hard to kind of visually classify even the land use patterns, right? And SAR is an extremely important sensor in the sense that it can do all-time all-weather mapping, right? Which is something optical cannot do, right? And the fact that SAR image looks so horribly bad it kind of has an implication that you need an expert to interpret it, right? And these experts are extremely limited. And if at all ever in our lifetimes we have to see satellite images, being a commodity that everyone can use it, we have to solve this problem of needing an expert to kind of interpret star, right? And one of the key ways in which fusing it with optical is useful is using the color information in optical and fusing it with SAR, right? So, how many of you have heard about these neural style transfer networks? So there are these kind of memes or posts where, there was a Starry Night by Van Gogh, and they kind of created Starry Evening or Starry Day afternoon by Van Gogh, or a snow. They took a scene of New York and changed its style to look like a starry night in New York, right? So that is basically something called as a style transfer, where you understand the style of one image and kind of transfer it to another image, right? So it's kind of similar, where you learn from optical image that what land use pattern can be represented by what colors, and you kind of try to render it using these GAN networks. So this is one of the publication. You can go to it. So I have taken the results from that publication. It just takes Sentinel-1 SAR images and tries to use cycle GANs to kind of color those images, and you can see. So there are obviously caveats because these are not very advanced and very matured methods as of now. They are still in research, but it kind of resembles to how the Sentinel-2 remote sensing images looks like for the same thing. Yeah. So okay. So what is that technology what is that version of GANs that I can use to solve this problem? So one of the best part about GANs is that there are so many different versions of them for so many different type of problems, and what you can do, you can permute and combine them to tackle a new kind of problem, right? So here I talk a little bit about cycle GAN, which can be used to solve the problem of this kind of rendering or neural style transfer, right? And then I'll show you how combining this with a different type of GAN can help you solve a totally different problem, right? And I think the second best thing that I really like about these GANs are the loss functions. There are like a bunch of loss functions, and you can choose them, right? So it's like a Lego block of generative networks. You can kind of permute and combine a lot of different type of GANs and a different type of loss function to create a whole network of your own to solve something, right? So what I have here is something called as a cycle GAN, right? So how does a cycle GAN work? It's very similar to vanilla GAN, right? The only difference is so here I have my input, right? And here I have a generator, right? So what my generator does, it takes my input X, which is let's say a SAR image, and it converts it into, let's say, something like an optical image, right? Or like not an optical image, but a colored version of SAR image, right? And I have a discriminator which has, kind of real samples of how optical image looks like, right? So one thing that I will just tell you, in neural style transfer there can be two things, right? Either if you have paired data or you have unpaired data. So what do I mean by paired data? You have SAR images and you have corresponding optical images, right? And generally this kind of data is difficult to achieve because of registration issues, right? And because the timing of the capture do not match each other, right? So there is a spatio-temporal mismatch, right? So getting extremely well paired data is like near to impossible for a lot of use cases, right? So what this solves is unpaired image-to-image translation, right? So you have SAR data of a totally different scene and optical data of a totally different scene. You don't need to have both the images over the same scene, same time, like that, right? So that's why cycle GAN is really special, because for us remote sensing scientists, we can take data from two different locations, two different sensors, and yet we can train a network which can render my SAR images. How it does that? as I was talking, till here it's more or less like a vanilla GAN where it takes a SAR image, and from a SAR image it tries to create a colored SAR image, right? But what it really has, it has another GAN here which tries to reconvert it back to the SAR image, right? So we went from SAR to optical and then went back to SAR, right? And when you go back to SAR, right, what you should get is the similar output, right, which is called as cycle consistency. If you complete the cycle of going from SAR to optical and back to SAR, right, your final output should be consistent with the initial output, right? And this is an extra term called as a cycle consistency loss that this cycle GAN adds, right? And you train it basically, so first you train it this way, and then what you do, you reverse it. So you take an optical image, create a SAR image out of it, and then you take it back to optical image, right? So these two combinations make sure that even without paired images, even with unpaired images, enforcing cycle consistency will help you stabilize and train the model.
Yeah.
Right. So there is one more part here, which is the identity loss which these people add. So what identity loss says, let's say you take the generator G, right? It is supposed to give you, let's say, colored SAR output, right? So if you give a colored SAR output to this network, right, it should give you an identical output, right? For a SAR image, it is supposed to give a colored SAR output, but if you feed it back the colored SAR output, it is supposed to give you the colored SAR output, right? So if I am feeding it the Y itself, right, it is supposed to give me Y, which is the identity loss, right? So and similarly for the generator F as well, if I am feeding it X, right, I should get an X, that's my identity. Right? So I think this is what I want to point out. You can create your own permutation of these generative networks, by adding, subtracting these blocks of generators and discriminators, and then you can add enforced constraint like this at a local level or at a global level to kind of tune them to get the results that you want them to. Right? Of course, there are challenges, but this is kind of a starting point. Next. Yeah, so this is the second use case of these generative adversarial networks in satellite data, right? So again, the why of this whole problem, right? Why do I need to do? I think everyone kind of here will agree that we need to do super resolution, right? Doesn't matter how high of a resolution we have, there is always a necessity to do super resolution, right? But why optical guided super resolution of SAR, right? One simple reason, because getting high resolution data in optical is more frequently available, and the sensor is more easier and cheaper to put up, right, as opposed to SAR. So in SAR, if you have to go from 1.5 meter resolution to 0.5 meter resolution, it's going to cost you much more than what it's going to cost you for an optical sensor, right? And similarly, if you have to go from 1.5 to 2.5, the cost is drastically going to decrease, right? And it's much easier and cheaper to put a 2.5 meter resolution SAR sensor in space than to actually go and, build a sensor of 0.5 meter resolution, right? And you already have satellites that can go up to 30 centimeter resolution in optical, right? Planet does it at 3.5, Maxar does it at 30 centimeter, all these things, right? So if I can just find a way, right, to super resolve SAR using the high resolution optical data that I have, it's going to solve a lot of problems for me, right? Even as data scientist, even as sensor manufacturer, satellite manufacturer, right? It's a very, very important problem to solve, right? And this is again one of the publications that has worked on this. It's still again at a very nascent stage. None of these have reached a maturity where these can be adopted and applied practically. But you can clearly see, especially in this example, this guy's tried to super resolve a Sentinel-10 image to 4x of its resolution, right? And it has performed much better than the other conventional ways of upsampling the images. Right. So yeah, so I think just stay with me on this one. So this is a extremely beautiful example on, so similar problem as we saw in a cycle GAN, right? In a image translation problem, right? We have when we try to do super resolution, right? Ideally, what you would want is to get low resolution samples and corresponding high resolution samples from the same area of interest on the ground, right? But it's a challenge to do that, right? So what I essentially want to do is to do some sort of a unpaired super resolution where I have low resolution SAR samples, high resolution optical samples, and I learn a way to improve the resolution of my SAR data, right? And I know that if I have to do an unpaired translation, right, I use a cycle GAN. If I have to do super resolution, the standard thing is to use a super resolution GAN, SR GAN, right? What I do, I combine these two, right? I put some constraint on it, and I build a network, right? So I think this is a very good example of it. What they do here is, so they have two different type of images, right? They have the cat images, and they have these castle images, right? So cat images, they only have in low resolution. They don't have high resolution pairs at all, right? But castle images, they have a high resolution data, right? So what they do here is, they downsample the castle images using some standard downsampling operations, and they create a downsampled version of it, right? But this distribution, which is created from some standard downsampling process, is still not similar to the distribution that this low resolution cat image is going to have. It's a bad assumption to make it, right? So what you do, you kind of create a cycle GAN here, right, to translate the cat images from this low resolution domain to this low resolution domain, right? So what you see here is again those two cycles, right? The generator takes the low resolution cat to a low resolution downsampled cat that looks like a castle. Then here is a discriminator that compares it against the low resolution castle. Then there is another generator that takes this castle to a castle which is similar to the low resolution domain of the cat, and there is a discriminator here, right? So overall, what this part of my network is doing, it's trying to translate the cat from its low resolution domain to the cat whose low resolution distribution is similar to that of a castle, which is downsampled using a standard methodology, right? Then what I have is, this is part 1 of the GAN, which is like the cycle GAN, right? The part 2, which is the super resolution GAN, right? So this essentially what has happened is you have kind of sequentially combined the cycle GAN with SR GAN in a sequential way. So what my SR GAN does, it takes the low resolution cat which my generator has generated, it upsamples it, right? And there is a discriminator that compares it with the original high resolution castle image that I had. That is part 1, right? Part 2, what it does, it takes the pseudo kind of castle image which is generated by this generator, it upsamples it, right? And oh my bad, sorry. So what SR GAN does, it first takes the cat image generated by my generator, it upsamples it, it takes this pseudo castle image, right? So what is happening is, after I have changed the distribution of my downsampled castle image, I feed it through my generator, right? And when I feed it through my generator, it again kind of changes the distribution back to its original low resolution distribution. I pass it through the SR GAN and I get an upsampled image, right? And this upsampled image, there are two different type of losses. So first is kind of the MSE loss that it calculates between these two images, right? So this is the one I get after this whole process has happened, and this is the original high resolution image. And the second part is the discriminator that tries to discriminate that, you know, which of these images has come from the original high resolution distribution, right? So all in all, the crux of it is that I'm able to take two different type of generative networks, combine it and put some constraint locally and globally, and I'm able to use it for a problem that it's relevant to me, right? Everyone with me?
Yeah.
Right. So, yeah, so the point here is that there are multiple such problems like this. So see, these are a couple of huge problems that have kind of bothered me for a long time, right? And I myself have tried to find some solutions to them, and I have, you know, seen a lot of people in a lot of conferences trying to get their way past these kind of problems, and I feel that they are extremely relevant from the point of view of a sensor developer or a satellite developer or a data analyst, right? There are a few more problems that I haven't addressed in this particular presentation. The one where you know, you have optical images with clouds and you use SAR to kind of restore the features of optical images. So that's it's not recoloring or regenerating or translating SAR to optical, but it's the feature restoration, right? The optical images is supposed to look like how it would have been without the clouds, right? So these are a few more problems, and these problems don't directly feel like data fusion, right? Because the image that we have in our mind of data fusion is kind of, it's a little bit of stereotyped, right? But here what I am doing, I am taking one domain, data in one domain, and helping and using it to kind of, you know, enhance the data in the other domain, right? And that is something which I'll also call as data fusion. Right? Yeah, next. Yeah. All the good parts I think I already talked about, but there are some huge problems associated with these techniques. So first thing is that you know, our job would have been really easy if we were getting paired samples of optical and SAR images which were registered beautifully on top of each other, right? But that's not the case, right? Because of the unavailability of the paired samples, it's extremely difficult to build or use GANs that, you know, work on these paired data, right? And the GANs that work on unpaired data, they are extremely complex. It's very hard to get convergence on them, right? And especially generalize them, right? Temporal mismatch, again another huge problem. It's kind of this is kind of an implication of temporal mismatch. So two images, if they are taken at different time, there are obviously going to be a lot of dynamic features that are there present in one image which are not there in the other image, right? And that will lead to a bad training for the GANs, right? Noise in the SAR image, so it's a third big issue that people are already trying to solve using deep learning, where there is a lot of speckle noise in the SAR image, and that's part of the reason why it's so difficult to interpret the SAR image, right? And that's the reason why it's so difficult to kind of, you know, solve any super resolution or translation problem with SAR images with, right? The noise in SAR image is extremely useful as well, because that makes SAR image what it is. It allows you to solve a lot of problems. But when it comes to visually being able to derive insights from the image, I think it's extremely brutal on the person who's doing the analysis. The last point is the limited availability of training data itself. I think we all know that beyond Sentinel-1 and Sentinel-2, if we want to get our hands on high resolution data set, it's an extremely tedious and hectic process, right? And beyond that, if you want to go, you generally don't think past that, right? So I think the data being not available is a huge concern as well if you want to go ahead and solve these kind of problems. Yeah, so I just kept a little bit description about galaxy space at the end. So Galaxy Space is a space tech company. We are building a constellation of multi-sensor optical and SAR satellites, right? And therefore the problems that I have shown you, right? What I believe is having multiple sensors on the same satellite will be able to solve quite a lot of problems, because you can get data which is temporally and spatially matched, right? But what it doesn't solve is problems from the software end. It might solve some of the problems from the data end, but the software has to mature, like, you know, something like transformers did in case of language models. Software part of it has to mature so that, you know, it can support that data and, you know, it can get to us where we want to, right? So I believe that whatever we are developing will kind of help the developer community, the software community to kind of mature these models to that extent, right? Based out of IIT Madras, we raised 3.5 million seed funding recently, 35 team of 35. And if you want to discuss about these topics more, or you know, want to reach out to me for any opportunities, please feel free. I'm happy to do that. Any questions?
You guys are also in Bangalore, or you're only in Bangalore now?
So yeah, I'll clarify that. So we are in Bangalore, our head office is in Bangalore and the whole team is in Bangalore. Right? But we are incubated in IIT Madras and we are still the incubators at IIT Madras, so that's why we say that.
So to meet you, it's in Bangalore.
Oh, you can come to our office in HSR anytime.
So your main focus is building the satellite, or is it the downstream task?
No, so the main focus is building the satellite, right? But there is always this gap, right? So I think the end layer is something like what Satcher is doing, right? Which is taking the data and kind of deriving the final insights out of it to serve some businesses, right? But even before that, you know, what are those data layers that you can develop that can enable these downstream businesses to make the best use out of that data, right? So if I'm giving them, let's say, a co-registered packet of optical SAR with clouds in optical and SAR, they use it. It's fine, right? But if I'm giving, let's say, one option as colored SAR, if I'm giving them another option as, let's say, restored optical image using SAR, right? These kind of data products will kind of help them or get that leverage to solve their problems better, right? So that's why I believe that this is an extremely unexplored segment, right? And it's either it's binary thing, it's either 0 or 1. You get the data or you get the insights, right? So I think there is some work which should be done in this to fill this gap.
I have a question. Yeah. Okay. So the challenges you said that there is no like temporal layer. Second challenge is when you show this slide. The second challenge is can you show that
temporal mismatch? Yeah.
So how about creating composites? So usually in community the optical is accepted. Optical composites are accepted. SAR composite is it accepted? Have you tried that before?
Composite in the sense you want to get temporal composites.
Yeah. So you are saying temporal mismatch. Like June 1 you will have an optical and June 5th you will have a SAR image. So that's a temporal mismatch. How about taking a June 1 composite? All opticals compositely created out for June.
Right. Right. I think that's a good idea. I don't know to what extent it will solve the problem, because the problem is that if I take multiple pairs, right, because so many things will be dynamic, I don't know to what extent the composite will filter out the dynamic nature in the two images, right? For example, if you take a composite for the June month in optical images, right, the things that are changing dynamically, like vehicles or let's say the water bodies, right, they will appear, their features will appear different in the composite, and in SAR the features will appear different in the composite. That's just a thought, right? It's definitely a good idea, and I'll go back and try it as well.
And in SuperGAN, the core thing which we are trying to do is to like scale the images.
Yeah.
So what about the panchromatic, pan sharpening?
Yeah,
I
so
believe Pixel is also doing the same to like deliver the high resolution images.
Right. So pan sharpening is a established way of super resolving images, but there are two caveats to it. One is that you need to have a very high resolution pan band. That's number one, right? The second thing is pan sharpening will only available from optical to optical super resolution. Right?
Okay. No, please do it.
Yeah, so most of what you discussed in the first half, right? So those are like the hard problems. So in terms of giving this sort of optical plus SAR product, which essentially could be registered, right, like by design on Galaxy satellite. So which parts are like the low-hanging fruit to solve in all these problems that you said? Like which can be like quickly done by just having this data set? Like do you feel like say temporary mismatch is zero? Probably. So, but in your opinion, like which are the things that can get quickly solved by just like having this data itself?
So you're asking for the use cases?
No, so the challenges that you stated, right? Like even if you can do say super resolution of SAR data with optical, or transferring from SAR to optical so that it's easily interpretable. So those challenges, and also all these four that you've stated, which of them is easier to solve with like a Galaxy type of product? Like just by the product itself being available?
These two challenges will definitely be solved if that's what you're asking.
Okay.
From these four, right? Yeah, these two challenges will definitely be solved. The third one will be reduced because we have an X band, right? And X band inherently has less speckle noises compared to other bands. But it would be a life idea that the noise will be completely eliminated. It's going to be there, and it's useful. It should be there, right? But whenever you want to remove it, you should have the tools and techniques to remove it, especially for people who want to do visual analysis.
So I'm also seeing that the fourth one, would it? This is again just thinking out loud. Is availability of this data set probably might make other types of SAR data more usable suddenly. So any other X-band SAR data could probably be, you could develop the model on this data set, then go back and like uncover all the treasures and older archive data or any other type of data. Then would you also see that like community sort of probably would just like burst in a flurry of activity once this?
I think it's hard to comment on those kind of things. It's hard to predict how community reaction would be on these kind of things as well, right? So I'm really not sure how it's going to pan out, but yeah, I definitely want to make this a reality.
Yeah. I just want to share, it might not be a question. The thing is, I was working for the project. The title was the effective combination of SAR and optical for crop classification. But once I saw the SAR data, I found out if optical is termed to be democracy, this is hypocrisy, and SAR is a versatile actor, and this optical is monotonous.
Yeah.
So once I pitched into the data, I got to know the various effects of the SAR, and from past 1 week I was frustrated. But this topic you rechrist it as the generative AI, which boosted up the confidence of how the SAR and optical could be combined in an effective way. But the noise part in SAR, the recent NISAR launch, which is having the dual frequency, would it have an effect on it?
So NISAR has L band and S band.
Yes.
Right. See, L band in my opinion will be probably even worse in terms of noise, right? But see, if you're doing something like a polarimetric analysis or interferometric analysis, the noise is the most important part. You don't want to skip it out, right? So that's with X band, it kind of enables a lot of visual interpretation based analysis, right? So if you go to probably Kepler space, right? What the people who are sending X band satellites, what they're trying to do, they're trying to make SAR data more visually interpretative, right? But that will not solve all the use cases that SAR data is meant for, right? So for agriculture, I would probably suggest you to look at some of the polarimetric techniques, right? Because there the noise becomes a leverage to solve the problems. Coming on the other question, S band, I am really not sure because I haven't seen any S band SAR data either from an airborne sensor or a spaceborne sensor. It might be there, someone has an idea, can help me out. But L band certainly not, the noise will be there.
I just have a plugin. So Satchel has a patent on optical reconstruction from SAR imagery using cycle GANs.
Yeah, that's amazing.
So we have patented that, and it actually came out as a necessity for us, like you said, like you rightly said. Our focus was on delivering insights from satellite data, and it was impossible for us to do that in monsoon season in India, right? Which is when the agriculture is at its peak, and we were not able to identify any of that.
Yeah.
So it came out of a necessity, but you can check out Satchel Cygnus.
That's amazing. I think if you already have that, then having a co-registered spatial temporally registered data will be extremely helpful for your use cases, right? But I think there are going to be people who are not like Satchel, right? And they would want to do these things, right? So I just want to enable them and propagate the knowledge to them that this is possible. Optical SAR is useful. If you do these things, it will be extremely beneficial.
Cool. Awesome. Thanks, Doctor. That was. When I walked in, I didn't think I look at equations or generative. It was not what I expected, but thanks for reminding me where I am at my technical skills.
I think that's why I asked people to go out and have a break, because I knew it would not be.
Thank you so much. That's really good.
Thank you.
So yeah, that sort of concludes our session number, event number 8 for the Talk Spatial. Thank you all for coming. Thank you for speakers as well. I'm not sure how the logistics was to reach on time and stuff, but it was worth it.
Thank you so much to Jyotsna. So when last time came here, these stairs are not here. So she arranged these stairs, this projector, and no, thank you so much for inviting, and it was a pleasure to be here. Thank you.
Yeah, if you're interested about the next set of events that's going to happen, just go to our website, it's talkspatial.in. We have a Slack group. We have links, everything on the website. So there's a Slack group that you can join. Discussions about whatever, any talks you're having, technical part of it, internship and career opportunities. People can post their own questions there, whatever. So it's an open Slack group. So just follow us along, and then we'll keep you updated on the next set of events that's going to happen as and when we get it. And if you also have space for hosting us, let us know. We'll be more than happy to come. That's it. We can try network or cool. Thank you.
Hey, was it this group or was it the previous group with Ujjwal? So there was some meetups, I think, in Kothandhapani and stuff.
Yeah, I think that probably might have been. We are not even met in Kothandhapani. Just thinking. Not yet. Maybe one day.
He was like, there's mosquitoes in Kothandhapani.
Yeah, probably.
Maybe not there.
Yeah, group photo. Oh yes, we have to take a group photo, so please, I don't know where.